Okay, so today we're going to learn about another type of wave called an electromagnetic wave. Okay, oftentimes we will call these EM waves. So the first thing we'll say is that they can travel through space. They don't need matter. Okay, so they don't need things like Earth or any kind of thing like that. They can travel in space where there's nothing there. Okay, they're made by vibrating electric charges, which we'll get into in the next unit. And they are transverse waves, which you remember is like the up and down motion. Okay, so the electric field and magnetic field are perpendicular to each other. So you can see how perpendicular just means one's up and one's down like that, and they kind of alternate. Okay, this is more just a conceptual thing. The next thing is that there's some properties of waves, of electromagnetic waves, that we have to know. Some things about them that are unique. The first thing is that for all objects emit EM waves. So if you want to increase the temperature of that, you need to decrease the wavelength. And we'll get more into that when we have some pictures here later. We also call the energy carried by an EM wave radiant energy. And we can know this by one of the things that emits a lot of the EM waves, which is the sun. Okay, because it provides warmth and sight. Warmth and sight, again, are just types of wavelengths. Okay. Now, some more properties are that they travel at the speed of light. Okay, so which is 300,000 kilometers per second, and we'll say that's also the speed of light. It's very fast. That's why we can't see light, the wave of light. We can just know it's there, right? So this is nature's speed limit. Nothing is faster than this. We don't know of anything that can go faster than this actual limit right here. However, the speed can change depending on the matter which it's traveling through, the medium. It's slower in solids and it's faster in gases. And that's similar to things we've seen in the past. Also, just kind of a review, is that distance from crest to crest is the wavelength, right? Like from here to here, okay? We're thinking this can come more three-dimensional, but if it was, just two-dimensional, you could say, okay, like that, right? So crest to crest, and then the frequency again is the number of wavelengths passing a point in 1 second. So at this point, you can say there's a wavelength of, so there's 1 hertz, because there's only one wavelength of this is 1 second. So the relationship between wavelength and frequency is that if f increases, wavelength decreases. Okay. So there's different types of frequencies or wavelengths, and we're going to start off with a low frequency or high wavelength. So the first one is, we'll say this is low, and this includes radio waves, and we can say that there are different types of radio waves. One of them is a microwave. Okay, and we use that to cook food. That's a bit easy one to understand. Another one is radar, which is just radio detecting and ranging equipment. And we use that, to track somebody's speed, to track, different things for that. Whoops, excuse me. And then the last thing is MRIs. It's another example, magnetic resonant imaging, and we use that to diagnose illnesses, and it helps us take pictures of the body. By shining these types of wavelengths, we can get an image that we can see with our own eyes. As we continue down the spectrum, we get some things that happen with waves that are a lot shorter and start to become a higher frequency. Thermal energy is produced with these types of waves. And this is things that, we can see where, so it helps us to understand that if the temperature increases, the wavelength decreases. So as my T goes up, my wavelength will start to become shorter, right? So an example of this is we use remotes, computers, heating and food at fast food restaurants. You know, those infrared goggles that you can see out into the night, and it'll show somebody's body heat being shown off. That is used with infrared waves. Okay. The next one down the line is visible light. So but we all know that this is a range that you can actually detect with your eyes. So color is just that your eyes react differently to different wavelengths. So every color that you see is a different wavelength. Oops. So for example, blue is a short wavelength and red is long, but white is all wavelengths. So if you blended all of these together, you would see all these colors. And so the next one down is, and we'll talk more about visible light here in a minute, but the next one down is UV waves. These are higher frequencies, much higher, which means that the wavelength is going to be shorter. Okay, so the more frequencies you have, the more likely it can travel further into solids, which, for example, your skin cells. And if that happens enough, it can distort the skin cells to where they won't function right, and that can cause cancer. It can be used in other medicines and other treatments to kill certain types of things like bacteria and other things, but the big thing is if you're out in the sun, eventually if you get too much of that over time, it can cause your skins to mutate, which is another way of saying you have cancer. And one of the most dangerous types are X-rays and gamma rays. And if you've ever been to the dentist office, you've ever had an X-ray done, you can't just continually keep getting these, because these can affect the how your body creates cells and how they form over time. So these have the shortest wavelengths and the highest frequencies. I'll just say highest frequencies. So it's almost like what that's saying is that this is a lot more impactful than this. Okay, imagine this would be like somebody's fist, okay, and this would be like somebody's just hand out flat. Okay, you can do more damage with something that's more dense than this, right? So this packs a bigger punch than this. Okay, gamma rays and examples of this are X-rays and gamma rays. Okay, so gamma rays are shorter than X-rays, so they're even more dangerous. Okay, for example, so the X-rays, they can provide images of organs, and they provide a much clearer one than anything else, but then gamma rays can kill and damage cells. And we'll talk more about what gamma rays can do and some of the effects that we've seen worldwide over the last 30 to 40 years as to what gamma rays have the capabilities to do. So here's the diagram, or the spectrum, or just a layout of the different wavelengths and frequencies. And so as you can see here is that this is a really big wavelength. If I did 10 to the third, that's like saying 10 times 10 times 10, right? That's a big number. So as you increase the frequency, that means the amount, right? Okay, so that means that the amount that you'll see in 1 second is going to increase as you go this way. Okay, so F increases as you go this way, so it gets bigger. But as the wavelength, as you go this way, it's gonna get smaller. And you can see here it goes from 10 to 10 to 2 to 1, and it actually gets negative numbers. And you can see that. I mean, the distance here might be, and you can actually see the distance calculated right here. But let's say it's 1. Down here, it would maybe be like 0.1. Okay, so you have to know the relationship between the two. And as you can see, we have examples here: FM radio, infrared, light, ultraviolet, X-rays, and gamma. And again, here's the same thing. It's giving it to you in another perspective. It's actually flipped it to where, and it's okay. It's just saying that this side's the bigger side and this side's the smaller side, but the same thing applies. The distance gets shorter, the frequency gets bigger. Radio waves, microwaves, ultraviolet, visible light, and X-rays, and gamma. Okay, and we're almost done. We're going to talk about some of the things that light waves can do, and some of the ways that we can use light waves to help create and do things. So light waves, so to see an object, a light must reflect off the object and hit your eye. It has to. You can't see anything if there's no light. Okay, which light again is just a wave, right? So opaque objects, they absorb and reflect light, and no light passes through. So that just means you can't see through these objects. They're thick. Okay, you can say they're thick. So translucent objects, and that would be like these up here. Translucent objects allow sunlight to pass through, but you can't see clearly. Okay, and that would be an example of that. And then transparent objects transmits almost all light. So you can see clearly through them, and that would be the example right there. Just depends on the material, how thick it is, that'll let you reflect it, or if it'll let it pass through. Okay, the next thing is that the reflection of light, we have to understand that light waves, they're going to abide by this law of reflection. So if all objects reflect the light, then why can you see yourself in a mirror but not in a brick wall? Okay, well, because the brick walls have a bumpy surface which reflects light in all directions. Whereas a mirror is very smooth and reflects mostly light back to your eye in one direction. Okay, it's hard for us to see because if we just stare at a brick and we stare at a piece of glass, our eyes just see, a flat surface. But if you actually went down on the microscopic level, you would see bumps everywhere. And if you've got something coming in, like light waves, okay, that means that they're going to bounce off if they see those bumps and those different things. They're going to start bouncing off in all directions, right? But light, if it's very clear, wherever it hits, it's going to bounce off just in the same direction every single time. Okay, and that direction will be your eye. Okay. So the reflection of light, all objects have some kind of something called an index of refraction, which is just talking about, again, refraction is, we're just talking about how much the speed of light is reduced when it travels to the object. So the higher the refraction, the more speed is slowed down. So if you slow down the speed of the light fast enough, you can actually start bending the light, okay? And we call that a prism. Okay, so it produces color because the light traveling through the prism bends based on the wavelength of light. Okay. So for example, sunlight, which is white light, it has all wavelengths. So longer wavelengths are refracted less. Okay, so that means that, for example, red bends the least. So rainbows, for example, they're just water droplets do the same thing as a prism. They bend the light and based off of the different wavelengths. And that's what you see. So color in general of an object depends on the wavelengths the object reflect. We're almost done. So the color of anything, so a red apple, for example, reflects red and it absorbs everything else. So it takes all those different wavelengths in and it bounces off. So pretty much it's like, if here's the apple, all these, here's blue, here's green, here's yellow, here's, all the colors of the sun, which is all of them because it's white. White's made up of all the colors. When they hit that apple, all of these are just going to get absorbed into the apple. But the only one that bounces off is red, and that's what we see. Okay, so black is when, for example, all of the wavelengths are getting absorbed. There's nothing that bounces off, and we see the result of that, and so that would be the black color. Okay, and so we can put things like called a filter, and we can actually make it so that the color of light is reflected based off that filter. Okay, so for example here, the normal color is this, but when we put blue in front of it, green and red, we see those colors because it bounces off to what we can see. And the last thing is that if we mix colors, we can use something called pigments, which is just colored material used to change the color of other substances, and the result from the different wavelengths of light, the pigment reflects. So all colors can be made by mixing these three colors, red, blue, and green, and that's what I want you to write down. These are the primary three colors. So as long as you can mix those other substances together, you can get different wavelengths of light. Okay, this is a longer video, but there's more content that needed to be covered. Make sure you've got all your notes down. If you have any questions, please pause the video and don't hesitate to ask. Thank you.